Princeton. Actually, she's originally from here, Berkeley. Alice got her PhD from here. So she's going to talk about compactness of conformally compact Einstein matrix.
Okay. So, it's a great honor for me to give a talk here. Okay. So let me begin the talk by explaining my title. So first, my setting is four-dimensional. This definition, of course, works for all n minus n dimensions. So I have a manifold which is n minus 1 dimensional, and I usually denote Mn to be the boundary of this manifold. And then I have a metric G, and I denote it by G plus, and I say it's conformally compact Einstein. CCE, if there exists a defining function on X, which is a defining function, rho is positive, rho equal to 0 on the boundary, and gradient rho is non-vanishing on boundary, such that this rho square G plus is compact. And then, as this explains, conformally compact. So multiplied by some function which decline to 0 on the boundary is compact. And then in my setting, I also say it's conformally compact Einstein. Then in that case, I assume G plus is Einstein. But in this case, this G plus, I also assume in my talk, is Poincare Einstein. It's Poincare Einstein. Maybe I can add the word Poincare there. That means resi of G plus is equal to minus n G plus. Satisfy this. So this is my setting, and I'm restricted to n equal to 3. And now, for this metric, suppose we denote this compact metric by G, and we restrict to G on the boundary. We call equal to H. And then my question is, what is the information of G on H affect the compactness of G? Okay. So this problem is modular conformal class in the sense that, of course, I can choose other defining function so that there's another G hat which is also compact. So the question is only well-posed modular conformal class. So in that sense, the boundary metric is defined on the conformal class of H. Because conformal class of H, I can use other defining function. I still have such a setting. Okay. So I forgot to say, I'm reporting on joint work with Yuxin Ge. All these are joint work. So my question is, when given a sequence of such metric, when is GI compact? When HI is compact. Modular conformal class. So that's the question I'm trying to address. So here is the theorem which we hope to get. Okay. So I start with a sequence of X4, and then there is this metric M3. This is the conformal infinity of the disk and the sequence of metric. So this is a sequence of CCE metric. Okay. And now there is already a compactification. So there is also already this Hj conformal class. So I choose a representative. Suppose Hj is the boundary metric. And I assume it's a compact metric in some class, which I'm going to fill in later, actually CK plus 3 compact. And then from there, I would like to say there is some representative in the conformal class of Gi plus, which is compact. I want to say, when is that true? And now, of course, I need to add assumptions, and I hope the assumption, the assumption I add are all conformally invariant conditions. I hope. Okay. So assume the following thing. So the first assumption we put it is, for that reason, we put it in oriented manifold. Then the first assumption we add is second Betti number of this X4 equal to 0. And then I add certain type of assumption. These are conformal invariant assumption. So I add it on the Yamabe metric, Yamabe class of this M of this Hj to be greater than equal to delta 1 greater than equal to 0. So this is the Yamabe class. So by that, I mean really gradient U square plus some constant times the scalar curvature U square on M. And there is this U, the volume form of U, 2n over n minus 2 power square. There is a constant there. This is the Yamabe constant. So it's a Sobolev inequality. So there is, I actually only need this to be positive, greater than equal to 0. So for that reason, for example, I can assume this Hj to be the Yamabe metric. Constant scalar curvature metric on the boundary. And I assume it's a compact family. And then I also need to assume some other condition. And one of the conditions I assume is this Yamabe constant of this Gj metric on the interior is also positive. So by this Yamabe constant, usually this y on x and the boundary x is defined to be inf of, there are two ways of defining it. You still inf over the scalar curvature, but you also add the mean curvature on the boundary. And then you inf, say, volume of the metric is equal to 1. Inf of this G hat is in the class of G. So it's still some kind of Sobolev trace, Sobolev inequality. And since I'm dealing with a boundary value problem, I also need to assume some other Yamabe constant is positive, and that I call the boundary Yamabe constant, and this is greater than delta 3 greater than 0. So this boundary Yamabe constant is the same as the Yamabe invariant, but instead of normalize the volume on the interior, I normalize the volume on the boundary. Volume of the boundary of this metric H is equal to 1. Normalize this. So this provides a Sobolev trace inequality. So this provides a Sobolev inequality, and this is the Sobolev trace inequality. Okay. And now, what I really hope is these are enough conditions to say there exists a representative in a conformal class of Gj, which is compact. And suppose that is the case, what is the most natural choice of the representative? Since I'm dealing with all these Yamabe problems, so the most natural representative will be the Yamabe metric. So we would like to say that this Gj, the Yamabe metric, is compact. That's what we hope to get. But in this case, the main problem is the boundary Yamabe metric, this Gjy restrict to the boundary. We don't know how to relate it to the boundary Yamabe metric. That is, suppose we have a domain, say a region. We can solve the Yamabe problem in the interior. We can solve the Yamabe problem on the boundary, but we don't know what is the relation. Okay. So I have difficulty relating this class, this boundary behavior, to Hj. So instead, we choose another representative. That representative, when one first look at, is not natural. But let me try to convince you it's a natural choice. Okay. So now let's Gj star to denote the metric. Which satisfies the following property. So we look at the Laplace of Gj plus of W. Say there's always index for each j equal to 0, equal to 3, n equal to 3 on x. Okay. And then this Gj star is equal to e to the 2wj for each j, Gj plus. And such that I can choose to solve this boundary value problem such that this Gj star restrict to the boundary is my Hj. This is solvable because we are in this compact manifold. And then the conclusion we want, so I need a third condition here, which I will explain later. The conclusion is Gj star is compact. So in Ck minus 1 alpha for some alpha less than 1. Okay, so that's the statement of the theorem, but I still need to explain what's the third condition. Okay, so now let me explain what is the third condition and what is this metric. And this metric has appeared in the study of some other object called renormalized volume in conformal geometry. And this metric has been used, introduced by Pheromone. So we call it the Pheromone metric in a work in around 07. Okay, so for other study of this subject. So this is the Pheromone metric. I want to say it's compact. Okay. And now let me fill in the condition 3 and also explain property of the Pheromone metric. For this, I need to fill in some other background of this topic. So let me say some background. Most of these background are true in all n-dimensional settings, but let me restrict it when n equal to 3. Okay. So first, there are a lot of examples of Sashimi manifold. An example of Sashimi manifold is, for example, the hyperbolic ball and with Sn as conformal infinity. Obviously, you multiply the hyperbolic, if you think about GH as equal to 1 minus x squared dx squared hyperbolic ball, then you multiply by this distance function. It becomes flat and compact. And then you also have an example of this quotient group. Okay. And in that case, these conformal infinities, Sn minus the limiting set of this. So there are lots of examples, and then there are other more sophisticated examples, which I will not mention here. Okay. So, and the question actually is, given M on a manifold Mn, when can you fill it in by a CCE manifold? Does there exist? Can one find this X such that M is the conformal infinity of a CCE manifold? Conformal infinity. And this question so far has no counterexample, but on the other hand, the only existence result is, for example, besides this typical example, one has the example of Jack Lee here, and Grant. They say that if on Sn, if you have a metric G, which is very close to the canonical metric, then you can fill in by a metric which is very close to hyperbolic metric, by a hyperbolic metric, existence result. So the basic fact in this subject is the following. So the basic thing is that, so these are examples. Okay. And then the other thing is there is this construction method of Pheromone and Grant. They say that given M, you can find a tubular neighborhood of M such that such metric G plus exists in a formal power series setting. Okay. So there is a Pheromone-Grant's work about existence on M cross 0 epsilon. Okay. And now, let me say a bit about the basic fact in here. Okay. So the basic fact is the following. That is, first, CCE manifold implies asymptotically hyperbolic. So the sectional curvature on the boundary is already close to -1. And then, if you have you already have a rho such that this is a defining function, then there exists, you can change this to geodesic defining function. There exists R, which is a geodesic defining function, such that if it's a CCE manifold, then R square of G plus in this distance function is in a neighborhood of the manifold is totally geodesic on M cross 0 epsilon, and such that its gradient R on this metric G is equal to 1 on M cross 0 epsilon. So I should say there exists epsilon positive such that this is true. So in an asymptotic neighborhood of M, it's totally geodesic. And using this, one can begin to, this geodesic defining function, one can power series expand this GR, and this GR takes the following form. You have the boundary metric, which is G restrict to the boundary, and then there is this power series expansion, and since it's totally geodesic, the first order term is 0, and then there's the second order term, and if we are in n equal to 3, we have G3 and so on. Say n is odd. When n is even, there is a log term appear. So let's say this one. For my purpose, I only care about the R3 coefficient. And then it turns out this G2 is decided by GH. It's actually the Shelton tensor of the metric H. So that by Shelton tensor, I mean the metric, which is 1 over n minus 2 and Ricci minus the scalar curvature over 2 to the n minus 1 GIJ. So this metric is just the Shelton tensor of H, G2. Okay. But it's also known that in this expansion, the information of HG3 does not come from H. Okay. The expansion G3, of course, is determined by G+, but there is a possibility there is a different G+ correspond to different G3. So G3 is non-local information, not determined by H. Okay. And so actually there is non-existence result by non-uniqueness result by Hawking-Page on the manifold S1 cross S2, you can have two different filling in. And that is, the H is the same, but different G3. And you correspond to different Poincare-Einstein metric. Okay. Non-uniqueness way to fill in. Okay, so now, given that, let me also mention there is also uniqueness result. The uniqueness result I know of is first by Chang in 2006, where he says that on this Sn, if the conformal infinity is Sn, this, fill in the G+ is unique. And his proof used positive mass theorem, so it only works for so far n less than equal to 6, but there is also the Dutta and the Javahiri result later, 2010, and which says this is in general true. So on the Sn, the result is rigid. And let me also mention the local uniqueness result of Becquer. And what he says is if H0 and G3, I mean Gn, when n is odd, and this is determined G+ in a neighborhood. There's a local version of this result. In a neighborhood, it determines this in a neighborhood, local result. Okay. So the question we are asking is, does this information really determine this corresponding conformal compact, the compactness result? So we want to say this representative is compact, and it compact depending on Hj, and it also depending maybe on the expansion of G3 information. So we want to capture what is that G3 information in this expansion. And for that, I need to talk about another analytic tool in this subject. So analytic tool is we want to play with some PDE so we get uniqueness. we get regularity. Suppose we have a metric which is in this G plus and which is compact, compactified metric. Okay. And then this is conformal to Einstein. We want to know that what is the PDE satisfied by the metric G. So it's conformal Einstein. And one of the well-known tool is to study so-called Bach equation, Bach-flat equation. And that is, in 4 manifold, we are studying the critical point of the Weyl curvature. This is the Weyl curvature. And the critical point of the Weyl curvature is Bach-flat. So this is Bach-flat, is Bij equal to 0. And that Bij is a second derivative of the Weyl tensor and plus the Shelton tensor, there is an index there, okay? So this Shelton contracted with Weyl. So there is this Bach tensor equal to 0. And so in a case when X is a closed 4 manifold, this Bach equation has been studied by early work of Tian and Wiatkowski. In a series of papers. And the key observation, one of the observations they have is using the relation between the curvatures, the derivative of the curvature, this Bach tensor, and assuming the scalar curvature is constant. This equation can be rewrite into an elliptic PDE. So in general, the equation is Laplace of the Aij is equal to A convolute with the curvature tensor, and then let me stress there is a term which does not appear in their work because this is 0 in their work. Okay. So when scalar curvature is a constant, then this Bach-flat equation is an elliptic PDE, elliptic equation, so they begin to study the regularity of this work. So our task is to understand this equation in the case where there is a boundary metric. And then, because our interior metric is not a scalar curvature Yamabe metric, so we also need to handle this extra term. That's the task. Okay. And now, what is the natural boundary condition of this elliptic system? Since this equation comes from the Weyl curvature in the interior, so the natural boundary condition should come from a conformal invariant quantity on the boundary. Okay. So that means we begin to study, sorry, I should use the other blockable. So we begin to study metric this is too dense. Okay. So we study the metric, the corresponding functional. When one look at the Gauss-Bonnet formula, one should study the functional is, I don't know if I can write on this. Sorry. So the metric one should study is the functional should correspond to the Weyl square on the interior plus some natural boundary term. And if one look at the Gauss-Bonnet formula, this is a conformal invariant term. The second fundamental form on the boundary, and then the Weyl in the normal direction. One study critical point of this functional. And then the critical point of this corresponds to what we call S equal to 0. Critical point is the S tensor. Okay, S tensor. So S tensor is the critical curvature of that tensor. And in this case, so this S property of S is trace of S is equal to 0. And then it also has the conformal invariant property. If you have a metric, this alpha beta is the tangential component, there is a rho of SH. There is a conformal covariant property of this S tensor. So this S tensor would be a natural tensor to study. And fortunately, this S tensor usually is a combination of the first derivative of Weyl. But in a Sashimi setting, this S tensor is equal to minus of the normal derivative of the Shelton tensor in the tangential component. So one look at this, one knows that this is a perfect match for this elliptic Pde, where Ij is all component, alpha beta is the tangential component. So this is a matching condition for that system. So the condition is a boundary condition for Bach equation, and then it turns out in a Sashimi setting, this happened to be our G3 of alpha beta. So the condition, and then this, because of the conformal covariant property, this S tensor on the boundary is a conformal invariant. So the most natural condition is now on the boundary, we also have an invariant condition. So the most natural condition to put on this black ball should be S in L1, uniformly in L1. Okay? But unfortunately, we haven't been able to do so. And what we have is a condition, the S for the sequence of this GJ plus this conformal compact metric, S tensor of this GJ plus sequence is weakly in L1, weakly compact. Okay. So for example, if this S tensor is in LP, uniformly in LP, for P bigger than 1, that's enough. Okay. And so under this condition, we reach the compactness. But now let me explain why Pheromone-Grimes metric comes in. So now the Pheromone-Grimes metric is the following metric. The key property of Pheromone-Grimes metric in this regard is, suppose we solve this W equal to N equal to 3, and then we look at the metric, which is E2W G plus. Then this metric on this satisfy the condition Q4 of the metric G star is equal to 0. So what is this Q4 metric? Q4 metric is some strange combination of the curvature. So there is a quadratic curvature R squared minus 3 rho squared, which appear in the Gauss-Bonnet formula, and then there is a Laplace R term there. And this metric, this satisfies this, is equal to 0. And using some conformal invariant property of Q4. But then why is it natural to take such a metric? And that's because of Gauss-Bonnet formula. So in this 4-manifold order X and minus X 4-dimensional manifold, and suppose we are talking about order characteristic, then we have this Weyl square, and then plus what I call Q4 here on X. Notice I artificially insert this Laplace R term, so there is a boundary term to cancel it out, and that's what the Q3 curvature, and then plus another thing, which is a pointwise invariant. This Weyl curvature is an invariant quantity, and so is this boundary. So the offshot is Q4 curvature plus the boundary Q3 curvature is a natural extension of the scalar curvature plus the mean curvature, but this is in the 3+1 setting. So the Pheromone metric has the advantage pushing Q4 to 0 and concentrate the behavior all to the boundary. That's what we want to get hold of. Okay. And in the Sashimi setting, since we are talking about totally geodesic boundary, this Q3, in general, the expression is complicated, but in this setting, it's particularly easy. It's just shifting this term to the boundary. So it's 1/12 dr d normal for this G star metric. Okay. So it's a very easy thing. Both, this is a non-local term, but which is the scalar curvature restrict to the boundary. So compare this to S3. Both, but the S tensor, both are non-local term. They sort of complement each other. Because if you trace of S is equal to 0, and it's actually the DD normal of the Shelton tensor, and this is DD normal of the scalar curvature. Both are non-local term. Okay. So now let me, with all this background, let me now sketch some proof of the theorem. Another key property of Pheromone metric is the following. So this is the Pheromone metric. Okay. One key property of it is that it is a scale. One observation is the following. So a proposition is the following. It turns out in this Sashimi setting, if on the boundary, this boundary metric is H, if the scalar curvature of H is positive, okay, then the Pheromone metric is a fourth order equation, and then we try to estimate it. We need some second order control, and it turns out in this case, this Rg is positive on X. The boundary positive Yamabe class implies the interior is Yamabe class, and one actually have this estimate. Okay, one actually have this estimate. And I don't have time to sketch the proof of this result, and this result uses early work of Jack Lee. Jack Lee says that in this setting, if the boundary Yamabe class is positive, then the interior Yamabe class is positive. Okay. And here we say this is positive. And in this case, one also can see this metric is just 6 of e to the minus 2w and 1 minus the gradient of g star of this EW squared. So the fact it's positive means this distance, this EW is compared to the distance of G star, the real distance. So this gives strong estimate of the metric G star. And in the rest of the talk, I will begin to sketch the proof of the result. I will sketch the part where it shows that there is no interior blow-up, no boundary blow-up. Okay. So the step 1 is actually motivated by the Tian and Vyakowski program and trying to get the epsilon regularity result. And using this Buck-Flat equation. And in that case, the tricky part is how to do the S tensor itself already control the behavior of all the other derivative of the metric on the boundary. So the S tensor is itself the normal derivative of the Shelton tensor. But later on, when you do the iteration scheme, you need higher normal derivative than this. And why is it all already controlled by the S tensor? And that's the content of this epsilon regularity result. So the statement is as follows. We say that under assumption of the theorem, and suppose the volume of the ball G star is greater than or equal to some constant times r to the 4th, non-collapsing. That's why we needed a positive Yamabe assumption. Then there exists an epsilon positive and a constant Ck positive if the curvature norm Rm squared of this ball is less than, say, epsilon naught square, epsilon square, then you actually have all the derivative of this Shelton tensor. First, you estimate its case derivative norm, and then you're trying to pass to the sup norm, and there is a Ck, and then r to the k plus 2, and then there is this a square, and then the thing which control all the boundary behavior when you iterate this, everything is controlled by S. And on this ball or PR restrict to the boundary and plus some power r to the 4th power. That's the iteration. Okay. And from there, one can iterate to get sup norm estimate in terms of this quantity. That's the epsilon regularity result. And then, after the epsilon regularity result, we follow the usual scheme of study proof by contradiction. Suppose the curvature bound does not exist, you begin to blow up. And let's study the blow-up limiting metric in a Gromov-Hausdorff sense. So that's step 2. is one begin to study, suppose the sup of this Rm of this Gi is equal to Ki squared, and then this is on my x at Pi the maximum happen at Pi, you begin to blow up Pi, and then you consider this G star is equal to the blow up sequence. Okay, it's blow up sequence. And then it tends to a limit. Okay. And this limit we want to show using this distance estimate of this metric Wi, this conformal factor. We study the limit. And the offshot is using this distance estimate, we can show that this Gromov-Hausdorff limit tends to a metric G infinity bar, and this G infinity bar also is conformal to Einstein. That is, this G infinity bar is also take the form of some function W infinity, and then there is a conformal Einstein metric. Okay. And now our task is to try to see where is the contradiction. And now here the assumption comes in. So the assumption to come in is the following. So we are using this boundary to push the compactness inside. So on the boundary, we assume this HA is compact originally. So when you dilate it by this such big factor, this H infinity is dx squared. And then this M infinity, which is the conformal infinity to x infinity and boundary x infinity, is actually R3. So we are in a setting that we have a not compact, but a conformal Einstein metric with boundary, the flat space R3. And then we try to say that why this already push G infinity plus to the normal hyperbolic metric and G infinity plus bar to the flat metric. That's the task. And so there are various strategies to do it. And one possibility is adding this condition 3 would imply that S tensor for the G infinity metric is identical to 0. Suppose you assume S is in LQ, then this is a scale property. And G infinity bar is 0. And then from this, we are in a situation of R3, and then the S tensor G3 is 0. That allows us to use the result of Picard. Okay? So plus the result of Picard, which says that this Weyl tensor is equal to 0 in a neighborhood. For each point, there exists a neighborhood such that this Weyl tensor is 0 on a neighborhood. And then, because we are in this conformal Einstein setting, we now can apply the unique continuation theorem. Notice that on this setting, we actually have this G infinity plus of Weyl. This is an invariant. We use this metric. Then the PDE is an elliptic system, but it's Rm with Weyl. So a unique continuation would say this is a result of a Rafe-Mazzero in this setting, but in a system, it's also early work of Calderon would say if it's vanishing, then this Weyl is identically equal to x on the whole x4. Okay. So in that setting, what we have is now, this means that we are pushing the situation. That means, well, G infinity is really the hyperbolic metric. And then we study need to, the last step is to study why the conformal factor should be trivial. That is a 2W infinity. And that boil down to an elliptic PDE. So if one write down the suitable conformal factor, we have the following PDE, say in R4 plus. And then which satisfy gradient U equal to Laplace U is equal to 0 on R3. And we want to say U is equal to 0. On any bounded domain, if this is not the upper half space, you will think U is already 0. But not in this case, because e.g. U is equal to YQ will satisfy this condition. So this doesn't push this conformal factor to 0. What saves us is this metric, the limiting metric, also have positive scalar curvature. So in that case, we also have the assumption that this is gradient U is greater than 0. So this last condition corresponds to the positive scalar curvature condition, and together this implies U equal to 0. Okay. And after that, what we mean is this G infinity bar is actually the flat metric on Euclidean space. So since we blow up at the point where the curvature is 1, that's a contradiction. That's a contradiction. So we reach the boundedness of the non-blow up of the curvature, and then we still need estimate the diameter. And the last step is to show the diameter of this GJ star is bounded. Okay. So there is a bounded geometry there, and we reach no blow up on the boundary. And that's the outline of the proof. Okay. So let me put some remarks on the whole thing. And as I say that this condition 3 is, we rather is to be S1, L1. If it's L1, there is some possibility you can eliminate that. There is some possibility. Okay. But well, at this moment, we do not know if it's L1. But this scheme shows that if we replace 3 by 3 prime, that actually there exists a number epsilon positive. This epsilon, depending on the delta 1, delta 2, delta 3, can be computed. And if the S tensor of the sequence of this sequence is less than epsilon, this particular epsilon, then it's compact. So there is a small neighborhood, the L1 norm suffices. And then, so this implies compactness. So we don't know if we can push this epsilon to be bounded or something. And then another remark is that it turns out that the condition 3 can also be replaced by some other condition. We have 2 non-local invariants. One is this Q3, the D scalar curvature, D normal. And the other is this tensor. And it turns out these 2 things are related. That is, if we can push the Q3 on the boundary metric, this boundary metric to be 0, this would imply S for this boundary metric is 0 in this conformal Einstein setting. So one may as well try to push this scalar quantity than the tensor quantity. So the condition 3 can also be imposed to make sure this happens. Okay? And the problem is, in this case, our scalar curvature is positive in the limiting case and equal to 0 on the boundary. So the limiting metric, this Q3 already has a sign. It's already less than equal to 0. So if our original sequence, if we have the negative part of Q3 of this GJ sequence if this is somehow scaled to 0, we are done. Okay? So this condition can also be replaced by this LP, P bigger than 1. And that's also enough for the compactness result. Okay? So, but we do not know how to push the limiting sequence to have this non-local quantity to be 0. That's part of our difficulty. Thank you. Oh, YB is, let me, I do not have time to say it well. It's a Sobolev trace inequality. The original definition is inf of all the scalar curvature G hat plus mean curvature HG hat, and then the volume of the metric on the boundary of G hat restrict to the boundary is 1. So the renormalized volume, so there is a power. So in this case, it's a 2 over 3 in the case of n equal to 3. So inf of this for G hat in G. But in our case, our base metric is totally geodesic. So it turns out this term we can ignore. Okay. So this is my formal definition of YB, so that it's a conformal invariant quantity. But in our case, it amounts to say that you have the Sobolev trace inequality. 2 thirds on the boundary is less than equal some constant, and then times gradient U square plus 1/6 scalar curvature U square on X. That's the inequality we play. Okay? And since this U is the conformal factor of our G star when we play it, and that G star is already Einstein, what we implicitly assuming is actually DUD normal on the boundary is equal to 0. So this is a Sobolev trace inequality we are playing. Okay. So there is an iteration scheme. Do I answer your question? Sure.
One question. I have one. Give us a counterexample of your compactness result.
I can't because counterexample, what do you mean? Okay. Because there are so few examples as far as I can tell. Oh, this is to prevent interior blow up. Interior blow up. And actually, that part of work is already contained in the early work of Michael Anderson for 4 manifold without boundary. If you want me to have a counterexample, I don't know what to say. I want second petty number to be 0. It's a sufficient condition. I do not know if it's necessary. Okay.
Okay. Now that is again.